Okay, so I have a program which I have written here for BiCMOS inverter. This is the ordinary inverter which we have already discussed earlier. Is it visible to you?
No, sir.
This text document is
Sir.
Okay. Is it visible to everyone?
Yes, sir.
Okay, so this is our ordinary inverter. It has one PMOS, one NMOS, then a load capacitor, and then an input pulse waveform that I am giving 0 to 5 volt with no delays. Okay, suddenly it goes to 5 volt, remains there for 1 nanosecond, and then it comes back and remains at low state for another 1 nanosecond. So the period is 2 nanosecond. 1 nanosecond is the high state where it is going to remain in the high state for 1 nanosecond, and then the period is 2 nanosecond. And I am going to run this simulation for 2 nanosecond. I am going to plot the transient response. So let's go to the terminal, and I will type ngspice inverter underscore dynamic. So this is something we have already seen. Only difference here is that I have given a very large load capacitance. So is this waveform visible to you? Okay, so you can see that from when the input goes from the red color waveform is corresponding to the input pulse, it goes abruptly from 0 to 5. Okay, in fact in 0 nanosecond, and then the output for that transition will go from high to low. But you can see that I have put a 50, since I have put a 50 femtofarad, okay, F for femto, I have put a 50 femtofarad at the output. Because of that, the transition from of the output from high to low is pretty slow. It is almost taking 1 nanosecond time. Is that clear? It is taking 1 nanosecond for the output to go from high to low. When the input for an inverter, when the input goes from 0 to high, output should go from high to low, but that high to low transition is happening in 1 nanosecond time. Okay, that's because there is a lot of charge stored in the capacitor. In that 50 femtofarad load capacitance, there is a lot of charge stored, and the NMOS device is turned on, and it is allowing that charge to flow into the ground. And as the current flows into the ground, the output voltage reduces. So this is a capacitor discharging waveform, the output waveform. Now when the input goes from high to low, then here you can see that the capacitor is almost discharged to 0 volt, but when the input goes from high to low, the output should now be charged to the high state, because for low state input you should have high state output, and it takes a time, almost again 1 nanosecond time. From 1 nanosecond to 2 nanosecond, it is charging through PMOS device. And since we have defined in our program, the PMOS is having the width double to compensate for low the mobility. So we have almost a symmetric charging and discharging waveform at the output. So the output gradually, it also takes 1 nanosecond to reach the high state. Okay, so this is with the 50 femtofarad load capacitance. I kept it purposefully large value of capacitance. Now in order to see how we can improve this, so everybody, keep this in your mind, this nature of this waveform. It is almost going from high to low over a period of 1 nanosecond, and it goes from low to high over a period of 1 nanosecond. So now I am going to close this, and I am going to run the other program, which is corresponding to BiCMOS. I have the BiCMOS spice program here. Can you all see this program?
Yes, sir.
Okay.
Yes, sir.
Okay. So if you look into this program, you can see the net list. The net list will contain few more additions. And what are the additions? You have two NPN transistors. Okay, there are two NPN transistors referred to as Q1 and Q2, and in addition to that there is one NMOS here and another NMOS here. So two additional NMOS transistors and two additional BJTs, which are NPN transistors. So there are four additional transistors, two NMOS additional and two NPN BJT transistors are also additional. So this you can, if you are familiar with this BiCMOS inverter circuit, so I will just take one circuit. So image, so yeah, can you see this circuit?
Yes,
Is it visible? Let me try to make it big. Okay, so this right side circuit is what we are talking about, this one. Okay, so how many NMOS are here? 1, 2, 3. 3 NMOS, 1 PMOS, 2 BJTs. So this is the circuit that I am implementing in the SPICE program. So parallelly I will put it side by side so that you can see the netlist and its corresponding circuit. So MP is your M1 here, okay, and VDD I have kept it as 2, ground is 0 volt, 5 volt is what I applied between VDD and ground. Okay, the terminals are 2 for VDD, not 2 for VDD, and 0 for ground. MP, which is M1 in this picture, okay, and this drain is here. I named it as node 3, okay, and input, that is the gate terminal, is node 1, and then VDD. So that is your source as well as bulk terminal. They are connected to node 2, which is VDD. So that is M1, description of M1 connection, which I've labeled it as MP here. And then next transistor is MN1, which is your M2, which is an NMOS transistor. Drain is 3, again same point, drain is 3, and then input is the gate terminal is at node 1, and then it is grounded. So ground is 0 node. Clear? Next is our M3, which I have labeled as MN. Okay, its drain is here, which this is a different point, so I labeled it as 4, and then input is 1, that is the gate terminal, and then you have the source, which is again a different terminal. I named it as node 5. This point, which is the base of Q2, I named it as node 5, and the bulk I have grounded. Okay, always in a CMOS circuit, always we ground the bulk terminal of NMOS, and we connect the bulk terminal of PMOS to VDD. Okay, the last NMOS is M4 in this circuit, and in the program it is referred to as MN2. So this is drain is 5, and then its base is connected to node 3, okay, which is the inverter output of this CMOS circuit, and then its source is connected to ground, and its bulk is also connected to ground, so 0 0. Apart from this 4 MOS device, we have 2 BJTs, Q1 and Q2. So I have named also Q1 and Q2. Q1 is the upper one, its collector is terminal 2, which is VDD, its base is node 3, which is the output of the CMOS inverter, and then we have 4, which is the emitter terminal. Similarly, Q2, you have a collector at 4, which is the output, and then you have the base at 5, and then you have the emitter grounded 0. And then I am connecting a load capacitor, which is same as that I shown in the other program, which is the normal CMOS inverter. I put 50 femtofarad. Here also I am putting 50 femtofarad, which is the load capacitor. That depends upon the next stage gate capacitance mainly, and also this node has some capacitance which you have already learned about. So now let us simulate this. So I am going to go into the program. I am going to type ngspice BiCMOS 1, which is our spice program. So here is the output. Remember your earlier waveform? I asked you to keep that in mind. It is the same scale. You can see 1 nanosecond here. This is in nanosecond. This is 1 nanosecond, and this is 2 nanosecond. Earlier waveform was something like this, right? It goes and almost reaches the low state. That is, the capacitor discharges only by around 1 nanosecond time. But now you see the output here is this yellow curve. Don't get confused with the blue curve. Blue curve I will explain a little later. So the output of BiCMOS is the yellow curve, and you can see that it comes to the low state in 0.2 nanosecond. Earlier it took 5 times larger amount of time. 5 times larger. This is 0.2 into 5 is 1 nanosecond. So it is like significant reduction in time for charging or discharging the capacitor in this case, because it is discharging through Q2, which is a BJT which can handle very large current when it is on. Okay, so the discharging time is significantly reduced to 1/5 of the CMOS discharging time. So that means, in other words, the fall time is now 1/5 of the fall time of the normal CMOS with the same load capacitance. Okay, now what is this blue curve? Blue curve is basically the output of node 3, which is the CMOS inverter output. This is a normal CMOS circuit. You give the same input, and if you take the output here, so node 3 is basically a CMOS circuit, but you see that here you don't have any load capacitance. So you cannot really compare this output with this output, that is the BiCMOS output. Why? Because there is no load capacitance at that CMOS. Okay, so it doesn't need to charge that large capacitance, 50 femtofarad capacitance, but it is without any load capacitance. The output of the CMOS is something like this. Okay, but if you put a 50 femtofarad at the output of CMOS, it will be much delayed. It takes more time. Larger the capacitance, it is something like if you have a big tank, it takes longer time for the motor to run and fill your tank. Something like that. Or if you have a tap, you're opening the tap, and if the pipe size is very small, it takes longer time for completely drain out the water in the tank. If it is a big tank, if it is a small tank, it will quickly get finished. So it's a capacitor can be treated like a tank which stores charges. So you are basically charging the capacitor or discharging the capacitor. So depending upon how big is the capacitor, it takes longer time. But if you can have a pipe which is a very big in size, larger pipe, diameter pipe, then that's what is BiCMOS circuit is doing. You charge and discharge the load capacitor through a larger pipe, or larger current flows, and so this yellow curve. Another thing, important thing you can see is that the low state is not really going into 0 volt like normal CMOS. If you have gone through the lectures, you will see why. Because, can anyone tell why the yellow or the orange curve is not reaching to 0 volt? Anybody? You are here or gone home?
There is no mechanism in this circuit for a reverse base current in the bipolar.
No. You look at this circuit. We are talking about this output. It is not going to 0 volt. You are switching on this transistor, but the voltage here, which is the voltage on the load capacitor, which is connected at this point, it is not going into 0 volt. It is not completely getting discharged.
Is it because of the VB?
Yes. So yeah, there is a VBE drop across base to emitter, which keeps the transistor in the active region. So without that VBE, you can't make the current flow, right? Okay, so because of that VBE, you can see that VBE drop, which is 0.7 or something like that. So that is the lowest voltage. So you can't have 0 low voltage state. It will be VBE. Similarly, you can see that charging to high state, same thing you can see, it is not charging to complete VDD. It is again there is a VDD VBE associated with Q1. Okay, when this output voltage reaches to VDD minus 0.7 or 0.8, till then only it will charge. So there is a cutting of voltages from VDD, and also the low state is not perfectly 0 volt. These are the disadvantages. The lecture makes it more clear, so you can go through it. So this is basically the simulation. Okay, any questions? So if you have laptop, you can run these programs. So it is already 12:20. I will close this, and for next week